Have a quick review of mirrors and lenses. A plane mirror will always produce a virtual image. As you can see here, the angle of incidence is equal to the angle of reflection. These angles are taken at normal, and no matter where the reflecting surface is, the normal will be 90 degrees to that reflecting surface. The magnification on mirrors is always 1, so the object is not any larger or smaller than the image. The distance of the object from the mirror is going to be equal to negative distance of the image, because the image is on the other side of the mirror. Images are always virtual for plane mirrors. Now let's take a look at concave mirrors. Concave mirrors are converging mirrors, and if your object is placed beyond C being the radius of curvature, or 2 times the focal length, your image is going to be real, inverted, and smaller. As you approach C, you'll notice that the image becomes the same size. It's still real, still inverted, but the magnification is equal to 1, or you could say that it stays the same size. As you can see here, as you get between the radius of curvature and the focal length, the object begins to become bigger. So it's still real and inverted, but now your magnification is greater than 1. Once you hit the focal length, what's going to happen is you're going to have no image. Once you get inside that focal length, your image becomes virtual, not inverted, and your magnification is more than 1, meaning the image is larger. Convex mirrors or diverging mirrors is a lot more simple. In all cases, the image will be virtual, not inverted, and your magnification will be less than 1, meaning your image will be smaller. Here are the equations that kind of govern that. 1 over the focal length is going to be equal to 1 over the object distance plus 1 over the image distance. Magnification is going to be equal to the image height over the object height, which is also equal to negative image distance over object distance. The sign conventions for the given quantities in the mirror equation and magnification equations are as follows. F is positive if the mirror is a concave mirror. You could also say converging mirror. So for converging optic devices, focal length is positive. Focal length is negative if the mirror is a convex mirror or a diverging mirror. The image distance is positive if the image is real, and it's negative if it's virtual. Real images for mirrors are on the same side of the object. Virtual images for mirrors are behind the mirror. Image height is positive if it's upright or virtual. Image height is negative if the image is inverted or if it's real. Here we have an example. A 4 centimeter tall light bulb is placed a distance of 45.7 centimeters from a concave mirror, having a focal length of 15.2 centimeters. Determine the image distance and the image size. So like all problems in physics, we're going to begin by the identification of the known information. So far, we know the object height to be 4 centimeters, the object distance to be 45.7 centimeters, and the focal length to be 15.2. Next, we're going to identify the unknown quantities that you wish to solve for. We would like the image distance and the image height. So to determine the image distance, the mirror equation must be used. The following lines represent the solution to the image distance. substitutions and algebraic steps are shown. So here's the mirror equation. This is a concave mirror, so the focal length is positive. The object distance is given and is positive, and we're going to find out what the image distance is. So we put those in the calculator. We're going to subtract on both sides, and then the number that we get here is 1 over the image distance. So we have to find the inverse of that. And if you're trying to find the inverse in the calculator, you just put 1 over the number and it gives us 22.8 centimeters. Now our number did come out positive, meaning it's real. So now let's find the new height using the magnification. Since we found DI, we can easily get magnification by doing DI over DO. So we're going to have the image height over 4 is equal to negative DI over DO. Multiply both sides by 4 to get image height by itself. And we put that all in the calculator. We get negative 1.99 centimeters, which means it's inverted, which makes sense because we just found out that it's real. So let's review refraction really quickly. When rays of light move from one medium to another, refraction occurs. The frequency of light will not change during refraction, but speed and wavelength can. Observing the equation V equals F lambda, where V is velocity, F is frequency, and lambda is wavelength. The index of refraction can be calculated by taking the ratio of speed in a vacuum, 3 times 10 to the 8 meters per second, and speed in a medium. That gives us the equation N, index of refraction, is equal to C over V, where C is the speed of light in a vacuum. Refraction also observes Snell's law, where we can see N1 sine theta 1 is equal to N2 sine theta 2. N is the index refraction of the medium. Theta is the angle that the ray makes with the normal. How objects appear through concave or diverging lenses. Now, concave lenses are diverging lenses, meaning that the ray will bend away from the normal, away from the principal axis rather, and spread out. In all cases, you get virtual images. They're not inverted, and the magnification is less than 1, or you could say the image gets smaller. Images on the same side of the object, as far as lenses are concerned, are all virtual. How objects appear through a convex or converging lens. So if the object is beyond 2f, it's going to be real inverted, and your magnification is less than 1, meaning it's going to get smaller. If it's at 2f, just like with the mirrors when it's at C, the image is going to be real and inverted, and your magnification is equal to 1, meaning it stays the same height. When it's between 2f and f, you can see that the image is still real, it's inverted, but now its magnification is greater than 1, meaning it gets larger. When the object is at f, there's no image. And when the object is between f and the lens, it's going to be virtual, not inverted, and your magnification is more than 1. Basically, the same situation happens with concave mirrors. So convex lenses and concave mirrors have a lot of similar properties because they're both converging. Lens maker equations are very similar. The only thing that changes a little bit is the sign conventions. F is positive if the lens is convex, So again, f is positive if it's converging, and f is negative if it's diverging, or you could say concave lens. The image distance is positive if it's real, again, except now with lenses, real images are located on the opposite side. Image distance is negative if the image is virtual, once again. Image height is positive if the image is an upright image or virtual. Image height is negative if the image is inverted or if it's real. Here's an example using a convex lens. A 4 centimeter tall light bulb is placed a distance of 45.7 centimeters from a double convex lens having a focal length of 15.2. Determine the image distance and the image size. So we're going to begin by identifying the known information. We have the object height, the object distance, and the focal length. And then we're going to identify the quantities that we want to solve for. We want image distance and we want image height. Let's get the image distance first. We're going to use the equation 1 over f equals 1 over object distance plus 1 over image distance. Here we have the focal length as being positive because it is a converging lens. We put those in the calculator, then we're going to subtract. After we subtract, we're going to find the reciprocal because what we just found is 1 over di. We want di on top, so we find the reciprocal of both sides, and we get 22.8. Very similar to the other example. Here we get the magnification so that we can get the image height. Image height over 4 is equal to negative 22.8 over 45.7. Multiply both sides by 4, and we get our image height of negative 1.99 centimeters. Now you'll notice that we got the same exact numbers for a convex lens as we would a concave mirror, so they are very similar.